All right, so in this video we're looking at complex numbers and emphasis on review here. Everything that you will see in this video should be a review of something that you've seen perhaps in a math course or another engineering course previously. But we're talking about complex numbers, and we're going to use the letter J to represent the square root of -1. Okay, that's called the imaginary unit. We don't use I in engineering because I is used for current in circuits, so we're going to use J. First thing you should know about J, or one of the properties, is the following. Notice that if I take J squared, right? J squared is J times J, so that's -1, the square root of -1 squared. So that just gives me -1. And then if I take J cubed, well, that is, I'll write it like this. That's J squared times J, right? And J squared we just said was -1. So this is minus J. And then if we take J to the fourth, well, that's J squared times J squared. That's -1 times -1. That's +1. And then if we take J to the fifth, well, that's J to the fourth times J. And J to the fourth is 1, so this is just J again. And we start over. We're back at J. So what we can say is we've got something like this. This is like the cyclic nature of the powers of J, where if we start at J, and then we can call that J to the 0, right? J to the 0, and we'll say J to the 0, or J to the fourth is 1. And then if we multiply by J, okay, then we would have J to the first. And then if we multiply by J again, so this would be J squared, that'd be -1, right? I'll write it as -1 actually. No, let's keep it as J squared. But we'll write down here this is -1, and up here this is +1. And then if I multiply by J again, I get -J. And then if I multiply by J again, I'm back at 1. Right, so in this direction, this is multiplying by J. You see that? So we can use this to evaluate higher powers of J actually. So like J to the 7th. J to the 7th. Well, here's J to the 0, J to the 1, J2, J3, J4, 5, 6, 7. That's actually equal to -J. J to the 113th. Well, I can write this as J to the 4th to the 28th times J. Right, because J to the 4th to the 28th is J to the 112th times J. And so that's J to the 113th. And why do I want to write it as J to the 4th? Because that's how many times around the circle we went. So J to the 4th represents one time around the circle. And so that to the 28th, J to the 4th is just 1. So that to the 28th, this is just 1 here. And so this is just equal to J. So I can always write a power of J as either 1, -1, J, or -J. Okay, and similarly, check this little trick out. If I divide by J, so if I take the number 1 and I divide by J, well, what is that equal to? I can multiply numerator and denominator by J over J, because J over J is 1. In the numerator, then I have J, and in the denominator I have J times J, which is -1. So this is just -J. So taking 1 and dividing by j gives me minus j. And if I keep going, you'll see I go around the circle in the other direction. If I took minus j and I divided it by j, I'd get minus 1. And if I took minus 1 divided by j, I'd get j, and so on. So this is dividing by j. Okay, so that's one thing that you need to be cognizant about, the powers of j. Okay, now we're going to talk about complex numbers, and a complex number has a real part and an imaginary part. And the best thing that you can do for yourself is to get used to representing complex numbers in the imaginary, or in the complex plane. So the complex plane has the real axis as the horizontal axis and the imaginary axis as the vertical axis. And so you can think of a complex number as a vector in this space. So for example, if I wanted to plot the complex number 1 plus j3. Actually, before that, consider this number. I cannot add 1 with j3. Like I cannot combine those numbers 1 and 3 because the 1 is real and the 3 is imaginary. And so this is as simple as a complex number can get. I just can't combine those two things. So I'm going to represent that as a vector where I go 1 unit over in the real axis, right? So that's 1. And then 3 units up because it's positive. And so I find that point. Here's the 1, 3. And so I can just draw it. I'll draw it in red. Draw an arrow like this. And maybe I'll label it Z. Okay, and so that's the vector z in the complex plane. Okay, this type of representation is called rectangular form. And if you think back to physics and vectors, or maybe Cartesian form, you may have heard Cartesian coordinates, but there are a couple different ways of representing vectors in the plane. So this is one of the ways where you have the amount that you go over in the horizontal direction, call that A, and the amount you go over in the vertical direction, call that B. So one way of representing a complex number is in rectangular form, A plus JB. But that's not the only way you can represent a vector in the plane. Another way is so-called polar form, or we're going to call it exponential form. These essentially, in our class, these mean the same thing, essentially, exponential or polar form. So what we can do, instead of telling you how far over and how far up and down the vector is, we can tell you the length of the vector and the angle it makes with the real axis. So we can tell you what the length of the vector is, r, and we can tell you the angle, theta, that it makes with the real axis. So in our vector here, z, the length of that thing is the length of the blue here, and then the angle it makes is this angle theta. So in rectangular form, how do you get the length of that vector and how do you get theta? Well, you should know from the Pythagorean Theorem that the length of the vector is a squared plus b squared. Okay, now an important point here is that notice in this calculation I'm leaving off the j. J only tells me the direction, okay? So j tells me to use the b, but I'm not going to use the j in this calculation. If I use the j in this calculation, I would get a plus jb squared, which, because j squared is minus 1, would end up being a squared minus b squared, and that's not what I want. Okay, so leave the j off in this calculation. A squared plus b squared, the square root of that gives me the length of that vector r, and then theta is the inverse tangent of the imaginary part b over the real part a. And again, I'm leaving off j in this calculation. Okay, so for example, maybe we'll express 2 plus j2 in exponential form. Okay, so that goes over 2 and up 2. So if I used the Pythagorean Theorem, I would find that I would have the square root of 2 squared plus 2 squared, okay, which is 2 root 2. And if I wanted theta, theta is the inverse tangent of 2 over 2. Okay, this would give me 45 degrees. Or we're going to use radians mostly in this class, so that's pi over 4 radians. Okay, now how actually do we express this given those two numbers? Well, the key is here the exponential. We're going to say 2 root 2 e to the j pi over 4. That is our answer. Okay, so just take a second, figure out what's going on here. That 2 root 2, that's the magnitude or the length of the vector. And pi over 4, that's theta, that's the angle of the vector. And so everything else is form-fitting. So we're going to take the length of the vector r times e to the j and then stick in the angle of the vector. All right, let's look at another one. Example. Express, how about j in exponential form? Okay, so j is pretty simple. It has a 0 real part. Actually, it's purely imaginary. So when I use Pythagorean Theorem, I would have 0 squared plus, and then the real part is 1 squared. So the magnitude or the length of that vector is just 1. And the angle is the imaginary part over the real part. So what's that? The inverse tangent of 1 over 0. Well, if you used your calculator you kind of plotted it, you could argue that it's pi over 2 radians. But I'll show you why that is. If we found, again, lean on the complex plane. If we found the vector in the complex plane, j is up here, 1 unit in the jth direction, right there. So what angle is that? Right? Pi over 2. Okay, so now we want to express our vector in exponential form. So we take 1, which I'm not even going to write, e to the j pi over 2. That's the answer. Okay, now let me erase this. Again, feel free to pause the video if you need. Moving on. All right, now let's say we wanted to add or subtract complex numbers. Okay, Well, you might remember from physics that adding and subtracting vectors is best done in rectangular form. So use rectangular form because vectors are added and subtracted tip to tail. So their components add. The real parts add, the imaginary parts add. So let me give you an example. Okay, let's say Z1 equals 3 minus J4 and Z2 equals 3 plus J4. Let's find Z1 plus Z2 and Z1 minus Z2. Okay, so Z1 plus Z2, remember the components add. So I've got 3 real part for Z1 and I've got 3 real part for Z2. So their real parts add 6. And then I've got minus J4 for Z1, imaginary part, plus J4, imaginary part for Z2. So they add and they make 0. And so the answer here is just 6. That's a purely real number. And let's do Z1 minus Z2. The components just subtract. So I've got 3 here, minus 3, so that's 0. I've got minus J4, and then minus J4, so that's minus J8. Okay, that's the answer. That's purely imaginary. All right, so let's move on. Actually, let's stay with addition and subtraction, but let's look at another example. Okay, how about let's say Z1 equals e to the j pi over 4, and Z2 equals 2e to the j pi over 2. Find Z1 plus Z2 and Z1 minus Z2. Okay, well, remember that when we add and subtract complex numbers, we're going to use rectangular form. So these numbers are not given in rectangular form. They're exponential, so we have to convert them. So I look at Z1 and I see, well, I can find this in the complex plane, actually. Okay, so this guy is a length 1 and an angle pi over 4. So do you know the coordinates of that guy? It's on the unit circle and it's got an angle of pi over 4. That's square root of 2 over 2, comma, square root of 2 over 2. Z2, so this is Z1. Z2 has a length of 2 and an angle pi over 2. So that's way up here. Angle pi over 2 is way up here. So this is just the point 0, comma 2. That's Z2. Okay, so when I add these, what the calculation I'm doing is square root of 2 over 2 plus j square root of 2 over 2. That's the first complex number. Plus 0 plus j2. That's the second complex number. So the components add. The square root of 2 over 2 plus 0 is the square root of 2 over 2. J square root of 2 over 2 plus 2. Well, I could get a common denominator if I wanted. The 2 is 4 over 2. So this is 4 plus root 2 over 2 times j. That's the answer. Okay, and if I wanted Z1 minus Z2, So I just subtract these two vectors. So I have the square root of 2 over 2 minus 0. That's the square root of 2 over 2. And j square root of 2 over 2 minus j2. And so this is j square root of 2 minus 2. If I get a common denominator, this is minus 4 over 2. This is the answer here. So that is adding and subtracting. Let's look at multiplying and dividing now. Multiplying. Well, because of properties of the exponent, same base, add the exponents. Dividing, same base, subtract the exponents. It's actually easier to perform multiplication and division using exponential form. So just to show you that, let's consider the general case where I have z1 is some length with some angle, and z2 is a potentially different length and a potentially different angle. z1 times z2 then would be r1 e to the j theta 1 times r2 e to the j theta 2. But look what happens. This is just r1 r2 e to the j theta 1 plus theta 2. So now my resultant vector has this is the magnitude of the resultant vector, r, because that's what's multiplying e, and this is the phase, or the angle, of the resultant vector, because that's what's multiplying the j and the power. So that's it. And z1 over z2, similarly, would be r1 over r2, e to the j theta 1 minus theta 2. You see? And so the magnitudes divide and the angles subtract. Well, that's pretty easy. Let's look at an example. Let z1 be the square root of 2 over 2 plus j square root of 2 over 2. And z2 equal, how about, minus square root of 3 over 2 plus j times 1/2. Okay, find z1 times z2 and z1 over z2. Okay, so we're going to use, I guess I didn't write it, but we're going to use exponential form. I said it. We want to use exponential form when we do multiplication and division. So z1 and z2 currently are not in exponential form. They're in rectangular form. So we're going to convert z1. Okay, square root of 2 over 2, comma, square root of 2 over 2, that's on the unit circle. That has a magnitude of 1, or length of 1, and it has an angle of pi over 4. So we actually just did this in a previous example. I can write z1 like this. 1 times e to the j pi over 4. And z2 well, z2 is on the unit circle as well. So do you remember what the angle of z2 is? So if we go over negative square root of 3 over 2, and then up 1/2, or somewhere over here, where this angle is pi over 6. So this angle is 5 pi over 6, I believe. Okay, so we can write z2 as 1 e to the j 5 pi over 6. Now, z1 times z2 then is just 1 e to the j pi over 4 plus 5 pi over 6. So you can get a common denominator of 12 there. So this is 3, and this is 10. So this is 13 pi over 12. Okay, so it has a magnitude of 1 and an angle 13 pi over 12. And z1 over z2 is 1 e to the j. Now you got to do the subtraction of pi over 4 minus 5 pi over 6. So this is e to the j, get a common denominator. So this is 3 over 12, and this is 10 over 12. So it's minus 7 pi over 12. And that's the answer. Okay, and there's one more thing I want to talk about in this video, and that is the complex conjugate. I think we've already seen the complex conjugate a little bit, but I just want to remind you that if we have the complex conjugate of a complex number, so let's say a plus jb is our original number, then the complex conjugate, which we write as z bar, is just a minus jb. Or if our complex number was in exponential form, it turns out the complex conjugate of this thing does not change the magnitude, it changes the phase, right, by negating the phase. So all you have to do is replace the j with minus j. So either one of these is okay. This is rectangular form, the complex conjugate, and this is exponential form, complex conjugate. And notice something really nice here, that when you take z times its complex conjugate, we'll do it in exponential form. So this would be r e to the j theta times r e to the minus j theta. This makes r squared. And then the e's go away because the same base, add the exponents, e to the 0 is 1. So a number times its complex conjugate gives you the length of the vector squared. Sometimes we call this length, we call this the magnitude of z squared. We write it like this. So let me give you an example. Let's consider z equals 3 plus j4. Find the magnitude of z using the Pythagorean theorem. And complex conjugate. Okay, so for A, Pythagorean theorem, I can find the length of that vector simply by doing the square root of 3 squared plus 4 squared. And that's a 3, 4, 5 right triangle, and so this gives me the magnitude is 5. That should be straightforward. But B, notice that if I take the complex conjugate of z, I get 3 minus j4. Okay, and then if I do z times z bar, it turns out actually that multiplying with complex conjugates is also easily done in rectangular form because something nice happens. Notice when I FOIL this thing, I do 3 times 3, then 3 times minus j4 is minus j12, and then j4 times 3 is plus j12. And then I have j4 times minus j4. Well, the 2 j's is minus 1, so that makes a plus 1, and then the 4 times 4 is 16. Okay, so the j's cancel, right? That will always happen when you take z times z conjugate. And then this gives me 25. And what we just showed up here was that z times z conjugate gives me the conjugate, gives me the magnitude squared. So now I know that 25 is the magnitude squared. So this means that the magnitude of z is 5. Okay? And finally, we can use Euler to convert exponential to rectangular. Okay, I think in a previous example, I gave the complex number, maybe we had 2e to the j pi over 2. Okay, and I kind of I plotted this and I made some arguments about, oh, the length of this is 2 and the angle is 90 degrees, but I just want to point out that we can say something like this. We can say, well, remember that e to the j theta, according to Euler, is cosine of theta plus j sine of theta. Right? That was Euler's formula. But look at what we have here. We've got exponential on the left, and then we've got real and imaginary on the right. So we've got rectangular on the right. So we can use this to convert between the two forms. So if I'm given 2e to the j pi over 2, I can use Euler's formula and say this is equal to cosine, 2 times the cosine of pi over 2, plus j times the sine of pi over 2. So cosine of pi over 2 is 0, and sine of pi over 2 is 1, so this is just j2. And we say, yeah, of course that's right, because if I looked at the complex plane, this has an angle pi over 2, and then a length of 2. So an angle pi over 2 and a length of 2 puts me up here at 0, 2. A 0 real part, right? And a 2 imaginary part.